Okay, so today I'm going to do those two topics which were like not clear: isomorphism, and matrix representation, right? So a matrix representation, when we were doing one thing which was not clear, I think, was when we are using non-standard basis. Okay, so these are the two things which I'm going to do it today. So to start with, what is isomorphism? Let V and So what my plan is that today I'm going to do the theory part of isomorphism and why we are using those non-standard bases. And then I have one more class on Wednesday. So we'll take a few questions for your practice. And then I'm sure you know that your assignment 4 has been shifted to Thursday, right? All of you know that your assignment
Yes,
4
ma'am.
is on Thursday, and then your quiz 2 is being shifted to 28th. Okay, so let V and W be vector spaces over F. Now there is one thing in like when we did vector spaces, and when we are saying that let V be a vector space, then what is a vector space? When it follows two properties, that it follows the addition and scalar multiplication. And then we say that the linear combination of that if there are two vectors, the linear combination of that vector will belong to that vector space. Now when we say that, when we talk about linear combination, then there are two scalars there, right? Whatever number of vectors, then we have those number of scalars. Now these scalars actually come from some field. So for example, there is this F field which is used in the linear algebra. So now those scalars come from that field. Now here when we are talking about isomorphism, now when we are saying that let V and W be two vector spaces, and we are defining isomorphic vector spaces, then we have to say that these two vector spaces are coming from same field. Right, let V and W be vector spaces over field F. A linear transformation T. I'm audible, right?
Yes, ma'am, you are.
Yes, ma'am.
Okay. Let V W is now let V be two vector spaces over F. A linear transformation is called isomorphism if T is 1 to 1 and on to. Now, actually, isomorphism is very important. That is why even if I want, I cannot leave this in your course, because the entire linear algebra is related to isomorphism, the linear transformation. Sorry. So this linear transformation cannot be completed if we are not doing isomorphism. So that is why it is to be done. So what is 1 to 1 and on to? So like for example, you have two vector spaces. Right now, if there are three elements here, and these three elements can be mapped to another vector space like this. If you have two vector spaces, this is a transformation, and you have two vector spaces. Now, if all element in V can be mapped to, because this is how we have defined the linear transformation. At what we are doing in linear transformation, we are actually defining a mapping from V to W, as I have given examples, so that if you have something, you can actually take it to another vector space, another space, like so that you can take R2 to R and so on. So like when we are doing it now, if each element in V can be mapped to W, then it is actually 1 to 1, right? And if this is a situation, like if you have 3 elements here and you have 4 here, now each element here is mapped, right? But this one does not have an image back in the another space. This one does not have an image in V. Now, therefore, this is 1 to 1, but this is not onto. Now, what is onto? That every element in W has a pre-image in V. That means this can be mapped. Now, what does that mean? So, for example, you have another example. This 1, 2, 3, and you have only 2 elements here. Now what is this? Now this one can be mapped here, this one can be mapped here. So this is an example of, this is onto, but is it 1, 1? Is it 1, 1?
No.
This is not 1, 1 because this element here, it cannot be mapped here because there is no element there. So this is onto because both these two have a pre-image, but it is not 1, 1. Right? So let V and W be vector spaces over F. Let T transformation is called isomorphism if T is 1, 1, and onto is the definition of isomorphism. Now, if there is an isomorphism between two vector spaces V and W, if there is an isomorphism from V to W, then V and W are called isomorphic. Now, why this is needed is because now when we are saying two vector spaces are isomorphic, it essentially means that V and W actually have same algebraic structure. It means V and W have same algebraic structure. Now in some application we are actually looking for spaces which have same algebraic structures. So that is why there this concept is used. Now it means V and W have same algebraic structures. Right now there are some important properties of isomorphism. Properties of iso.
Ma'am,
Yeah.
can there be a linear transformation like the third example which you gave?
There can be linear transformation. For this
Like
example,
the third one.
here,
Yes, ma'am.
yeah, there can be linear transformation because if you are going from R3 to R2, for example, because this is in R3 and you are going to R2, there can be linear transformation, but this is not onto, therefore this is not isomorphism. Now at this point of time, we are actually looking for those vector spaces which are isomorphic to each other. And one more point of onto, like when we are doing this isomorphic, why we are doing it? When we say that this point can go back to here, it essentially means when you are going from here to here means there is a linear transformation. When you are going here to here, it actually essentially means that T inverse exists. So when we are talking about isomorphism, actually it is saying that when it is onto, it means that you have a pre-image and therefore this T inverse exists. So now that's how this isomorphism and invertible matrices are related to each other. So that's what I have to do today. Properties of isomorphism. That's the first property, that for any linear transformation, I'm just writing LT, okay. For any LT, T V2W, T0 is equal to 0. Is it true? When you are proving a linear transformation, then you will prove those two properties, that it preserves addition and it preserves scalar multiplication. Then actually it means that T0 is 0. Now if T is isomorphism, then TV equal to 0 implies V is equal to 0. Right? And second property says, if this is very important, if T is in Moodle, I have actually uploaded one document which was talking about linear independence, and somebody has raised this question also in tutorial. Now, if T is an isomorphism, just okay, one question. If you have a linear transformation from TV to W, now tell me, then that transformation, when we are going, if V is independent, then TV will be independent. And the converse, if TV is independent, V is independent. Which one is true? So if you have a simple linear transformation, not my isomorphism, if you have a linear transformation, if if V1, V2, Vn are, if Vi's are independent, if these are independent, then TVI's are independent, right? If VI independent, then TVI independent. Is it true or converse is true? If TVI's are independent, then VI are independent. Which
Converse
one
is
is
true.
true? Why?
Converse is true. Because
And the
ma'am,
why?
TVI is independent than
Yeah, you are right. Yeah, this is how it is. That converse is true. Like if TVI are independent, then we are sure that VIs are independent. But if VI independent, it is not always true that TVIs are independent. But in case of isomorphism, this whole thing becomes true. Now we are doing the proof. If T is a linear transformation from V to W is an isomorphism, and S is a, and also in my slide somewhere I was using B and B dash. What actually I meant is, like if B is a basis in V1, V2, and I have used this B dash in a basis in W. So these were two notations I was using. So B and B dash. So suppose here B is a basis, V1, V2 in V, and B dash is a basis in W and this. So theorem says if this is an isomorphism and S is a linearly independent set, if S is, or B, if B is a linearly independent set, then prove it. Then TS or TB is a linearly independent set. Then TB, which is actually defined as TV1, TV2, and TVN. There is one more property of isomorphism, that I'm just writing this is actually a theorem. Two finite dimensional vector spaces are when they are defined over the same field, then they are isomorphic if and only if they have same dimension. So when we are generally defining these two, V to W, and we are talking about isomorphism, then these V and W, they are actually of the same dimension. So that's why I'm taking this N and N here. Right, so question is, if V1, V2, Vn is independent set, then prove that TB, which is TB1, TBV2, TBVN, is also linearly independent. Yeah, because other way around, we know it is true. How will you prove? So what I'm saying is linear transformation preserves linear independence if and only if it is isomorphism. From V to W, this way will be only true if it is 1 to 1, and both other way it will be true without 1 to 1. And also one more point, like when we are talking about isomorphism, if they are of same dimension, so 1 minute, I have to write this theorem because it is very important theorem. Theorem says two finite dimensional vector space. You till then you can just try if you are able to prove two finite dimensional vector spaces are over the same field F are isomorphic if and only if they have the same dimension. I have a proof for this. If and only if they have the same dimension. Two finite dimensional vector spaces over the same field are isomorphic if they have the same dimension. Okay. So that what I'm saying was that if they are of the same dimension, if V and W are of the same dimension, means they have 3 elements here, 3 elements here, then when we are proving isomorphism, then in that case, if instead of proving both 1 1 and onto, if we are proving only 1 1 or we are proving only onto, that will also suffice, because if it is 1 1 and they are of same element, then it will be onto also. And or if it is onto, then it will be 1 1 because they are of the same dimension. Therefore here we are saying that to prove this linear independence, the above one, if I am proving that V is linearly independent, prove that TV1 TV2 are also linearly independent. So in that case, if we just take that if it is 1 1, then it will suffice, because we are assuming that they are of the same dimension. Yeah, tell me the proof. Okay, so proof is if T is 1 1, since it is 1 1, we can write this, right? Since V1 V2, so this is because it is 1 1, because it is 1 1, and because this is because V1 V2 Vn are independent, therefore all alpha is as 0. This is the proof, right? The other way around, it is true. A true or means it is trivial, right? So this is clear.
Yes, ma'am. Ma'am, I have a
Yes.
question that what is
Yes.
difference between the bijective linear transformation and isomorphism?
Yeah, bijective linear transformation is not there in the course. So we have only isomorphism. So when isomorphism is when you have both 1 1 and on 2. And bijective is, I think it's only when you have one. So that is not there. We just have when you have to have both the things.
Okay, ma'am.
Yeah, so this was the proof. And there is one more thing. one more important, yeah. So in the exam, for exam purpose, when I'm saying that prove something is 1 1 and onto, there can be many methods to prove it is 1 1, right? So for example, if we want to prove something is 1 1, we can actually, so there is one method which other people are using. So if you have to prove something is 1 1, then you will take TV equal to, I mean, two vectors if there, so you will say Tx equal to TV, Ty, and then you'll try to prove that x is equal to y for 1 1. And then when we are doing this, there are some methods to solve those, like then they become the simultaneous linear equations, and then people are solving it in this. So all those I'm not doing it. If in the exam I'm asking if it is prove something is 1 1, then I'm just using one important result which through which you should be able to prove that it is um, 1 1. So this important theorem is this, and we need the this theorem's proof also. So this is what I'm doing. Theorem, let V W be a linear transformation, then T is 1 1 if and only if kernel T is 0. What is kernel T?
Nullity of T.
Dimension of null space.
What is kernel of T? Kernel of
Space of
T,
T. All
yeah, Tx equal to 0, wherein actually x is 0. Solution. So you will try to find the solution space and the values of x if they are x equal to 0, right? Now there is a proof for this. Can you try? Let this be a linear transformation. Then T is 1 to 1 if and only if kernel T is 0.
Ma'am, yes, this can be proved like if it is a linear transformation, then T0 equal to 0, but it is also 1 1, so we should be equal to 0 only.
And the other way around?
I don't know the other way around.
Okay. So proof. Suppose kernel T is 0. Right, so we are proving, suppose kernel T is 0, we are proving it is 1 to 1. Now, for 1 to 1, if Tx is equal to Ty, that's what I was saying. Generally, people do this. Like if you have to prove 1 to 1, then you say Tx equal to Ty imply x is equal to y. Right, now if Tx equal to Ty, then you can write this. This can be written because of linear transformation. This property holds. Now this is actually in W. Right, and this implies x is equal to y, because I just did somewhere Tx equal to 0 means Tv equal to 0 implies v equal to 0. If it is a so this is a property of isomorphism, that if T is an isomorphism, then Tv equal to 0 implies v equal to 0. So this is one way, then x equal to y, and therefore this is 1 to 1 because Tx equal to imply x equal to y. This is 1 to 1. Conversely, suppose this is 1 to 1 and x belongs to kernel T. Then Tx is 0 by definition. This can be written as T0. This is because X is 1, 1. So kernel T0. Yeah, so this is the proof. So now what I'm saying is that there can be two ways to prove something is isomorphism. Then it can be 1, 1 and on 2, but if they are of same dimension, then proving one thing is enough. And then if it is like, if you are saying prove something as isomorphism and you are saying just proving 1 to 1 will be enough, then either you can say that Tx equal to Ty implies X equal to Y to prove something as 1, 1. But in some cases, when you have big matrices, this will boils down to solving the linear equation. So instead of that, you simply can say that if it is 1, 1 you want to prove, you simply can prove that kernel T is equal to 0, and that will also suffice to say that it is 1, 1. Yeah, so that's what I was saying. And now there is another proof. I have that proof, but you can just try theorem. The one which I just said, that if V and W are isomorphic, if V and W are isomorphic, then it is actually both sides if and only if dimension of V is equal to dimension of W. Like, so if V and W are isomorphic, an important result says that their dimensions are equal. Now there is a proof for this. Can you try? So when I'm saying if and only if, it actually means you have to prove both ways. Yeah, just try this.
Ma'am, I had a doubt that if we are saying that if they both have same dimension, then proving 1, 1 or onto one condition is sufficient. So, so when there is no chance of having different dimensions, so we can always use any one of the conditions.
Yeah,
Okay, ma'am.
that's what I'm.
Thank
So even from here, one important thing comes out is when you are saying this V and W are of same dimension, then only this inverse will exist, right? Now, if you are on from R2 to R3, can you say that this transformation is invertible? There is one more thing that was there in my slides. I have written somewhere T is invertible, and there are three things which are equivalent. You just see it is written. There are three things which are equivalent. T is invertible, T is isomorphic, and T is A is invertible. Now it actually means T is invertible when T is isomorphic. So what I'm saying is that when you are going from V to W, and if they are on the same dimension, then it is sure that, right, T inverse will exist. Because this way you can go. So then this isomorphic and invertible are equivalent. And when if they are isomorphic, they will be of same dimension. So my question is, if you are going from V to W and this is R2 to R3, will the transformation T will be invertible? There are questions for invertible also I have to do. But before that, I just want to finish this. Yeah, tell me. So I am coming back to this invertible thing. So yeah, tell me how you prove that they are of same dimension. Okay, proof. If V and W are isomorphic, then the dimension are same. Okay. Now, if V and W are isomorphic, there exists a linear transformation T from V to W, which therefore this linear transformation, sorry, if V and W are isomorphic, there exists this, therefore this is linear 1 to 1 and onto, right? Because this is a linear transformation, so they are saying that if V are isomorphic, there exists a transformation T V to W such that it is linear 1 1 and onto, right? Therefore, by rank nullity theorem, what is rank nullity theorem? What is rank nullity theorem?
Rank plus nullity is equals to number of columns.
Yeah, so which is actually means dimension of nullity plus dimension of range T is equal to dimension of V.
Yes, ma'am.
Yeah, and since it is, we are saying if V and W are isomorphic, therefore it is 1 1, and from the previous example, it is kernel T is 0. Therefore, this one is D0. Yeah, so this one is 0. Therefore, we have dimension of W is equal to dimension of V. First part. Converse. Yeah. Tell me how to do converse. Suppose dimension of V is equal to dimension of W. Now what it is mean is, yeah, can you tell me how to do this? Suppose their dimensions are same.
So the dimension of the null space of T will be 0.
Why?
Because of the same rank nullity theorem.
No, but that in that case it was isomorphism. Therefore, we know that it was 1 1, and therefore kernel T was 0. But now we are proving that suppose, I mean, their dimensions are same, and we are proving that it is 1 to 1 or on to.
Ma'am, so dimension of the null space of T won't be 0 over here.
Why? Why it will be 0?
Like just following the steps you have done in the above question, above proof.
In above question, I am taking this dimension of nullity equal to 0 because it is actually 1 1. And if it is 1 1, the kernel T will be 0 from here. From the previous example. Here. Kernel T is 0 if it is 1 to 1. Here. So that's why I said that this becomes 0 and therefore both are equal. Now we have to do the opposite. If the dimensions are same, how we can prove it is 1 to 1? Because their dimensions are same. Therefore 1 to 1 and on to, we can just take one of it. So then we'll say just 1 to 1. Right? So suppose the dimensions are same and let B is equal to V1 Vn be a basis of V and B dash Wn be a basis of W. Right? Now, actually, that thing, that linear independence, right? So T preserves linear independence. T preserves linear independence if it is isomorphic. That is also because if it is isomorphic, their dimensions are same, and that is why we are able to prove the linear independence. That there is one document I have uploaded in Moodle. It is saying that if V1, V2, Vk are independent, the V1, V2, Vk will not be independent. Why? Because if there is no isomorphism, then these will be of different dimensions, these two. And then in this example, they are taking actually from R2 to R3. And when you are going from R2 to R3, a basis like 1001 will be independent in V, but if you take TV1, it is actually going in R3, and therefore they're showing it is not linearly independent. That is why this whole thing of preservance of linear independence becomes true only if it is isomorphic, because they are of the same dimension. That's why we are actually able to prove that linear independence. Now let this be a basis of V, and V is the basis of W. Right, since their dimension are same, so it is enough to prove it is 1 1 or on 2, right? 1 1 or on 2, they are of same dimension. Now rank T, sorry, range T. What is range T? It is actually span of TV1, TVWN. It is actually equal to span of W1, WN, right? Now because this is W1, W2 are bases, because we are saying it is basis, this span actually becomes the whole of W. Right? What we are proving? We are proving if the dimensions are same. If the dimensions are same, then we are proving that they are 1 to 1 or on 2. Right? So this is the basis. This is the basis. So it is enough to prove it is 1 1 or on 2. Now range T is actually your this W. Then tell me, how do I prove that it is on 2? This is actually V, you are V here, W is here, and your range is entire W, this. So it is like that, span of yeah, this is something like this, like you have two vector spaces V and W, and their dimensions are same, so they are actually both n, and we are saying that to prove it is isomorphism, I am trying to say that it is 1 1 or on 2, 1 will be suffice. So if I say take it as on 2, what actually on 2 means that all the elements here will have an image here. Right, so I'm saying this because the range is actually nothing but span of these elements, and thus W1, these n elements are spanning this entire W. Therefore, and because V is also n space, therefore everything will have an image here, because that is also a basis, that therefore it will be isomorphic, something like this. Yeah, so that was it about isomorphism. Next class, I'm actually taking more example. There is one more small thing I have to do, is about the matrix representation using non-standard basis. Was not clear, non-standard basis, right? So I'm saying that you have a linear transformation V to W, be a linear transformation, right? Dimension of V is n and dimension of W is m, right? And B is a basis for V1, V1, V2, Vn, and B dash I'm using is the basis for m, be a basis for W. This is basis for B, this is basis for W. Now we have seen that if it is the case, then we can write this TV1 as a linear combination of elements in B dash. So A11, W1, A12, W2 can be written as 1M, WM. Now this linear combination thing, I am just going to use it, so that's why I'm telling you. So then again, TV2 can be written as linear combination of and therefore it actually makes a matrix which is a m cross n matrix with wm. Now when we are doing this, what we were doing earlier, this tv1 can be written as a matrix form which is m cross n matrix, and there you have these basis functions, right, where these aij's actually belong to field, and I is 1 to n and j is 1 to m. Now question is, find the matrix. If you know that how from transformation we go to matrix, find the matrix for LT defined as R cube to R2 T x y z equal to x minus 2y 2x plus y. Now you have a linear transformation defined, and can you write it as a matrix form? Now how will you write? If I am using standard linear basis functions, right? So if I am using standard basis function, then I know that this t100, t010, and t0001 can be written as, from here, if I put x, y, z 100, then this becomes 1, 2, minus 2, 1, and 0, 0. Right? So therefore, this reduces this to a matrix form 1, 2, minus 2, 1, 0, 0. This will go as 1, 2, minus 2, 1. This we have already done. From where it has come is this 1, 0. This 1, 2 actually is coming from here, and then you can write as a linear combination. This we have done. Now, if I have to take standard basis, how we are doing. So question is, find a matrix for linear transformation R2 to R2 Tx1 x2 is defined as 2x1 minus 2x2 and minus x1 plus 3x2 related to basis which is not standard 1 0 1 1. Yeah. So how may you make the matrix out of this? So for this I need T10. What is T10? T10 is, if I substitute here, I get 2 minus 1. And T11 I get is 0, 2. If I substitute here. Now this, in the previous thing when we are writing, we can write this TV1 can be written as linear combination of basis vectors, right? So this is actually can be written as 310 minus 111, and this can be written minus 210 plus 211. Here, this is coming from here. So if you have a linear transformation from V to W, now any element TV1 can be written as linear combination of W1, W2 and Wm. If this is a standard basis function, then this becomes very easy because you write T100 as a linear combination, and writing 100 is easy. Now if it is non-standard basis, then also we are using the same thing, that you are writing this V TV1 as a linear combination of these, and therefore here I have T10 and T11. So if these two are coming as, if I substitute in linear transformation, this is actually 2 minus 1 and 0, 2. This can be written as linear combination of those non-standard basis function. Writing in basis function was very easy, but even if it is non-standard basis functions here, right, you can write, because these are basis functions, so that can be written as a linear combination. So that 2 minus 1, I am trying to write it as a linear combination of these two, and this you can simply see, right, how you will write 2. 2 can be written as 3 minus 1. So I am writing 310 and minus. and minus 1 can be written as 3 and minus 1. This is right? Yeah. So then this becomes 3 minus 1, and this becomes minus 2, 2. And therefore you can write A matrix as 3 minus 1 and minus 2, 2. That's the only difference when you're writing it as a linear combination. So you can just try one more question, then maybe it is clear. Now let T is a linear transformation from R2 to R2. So these are matrix representation of a linear transformation. X1, X2 is equal to X1 plus X2 and 2X1 minus X2. Let this be a linear transformation. Now find a matrix, find a corresponding matrix related to basis. B is 1, 2, minus 1, 1, and B dash is, now what it means is 0, 1, 1. You have a basis in V and you have a basis in W. So these two bases are given. How do you convert this T matrix in the A form? So what I'm saying is how do you write T1, 2, and how do you write T minus 1, because these are the bases in V and these are the bases. So you will write T1, 2. You just have to understand that you have two bases. One is in V and one other basis is in W. Whatever the question is, you will always write TV1 as a linear combination of basis function in W to get that matrix A. Now, if the basis function in V is not given, you will take a standard basis function and you will say T10 as a linear combination of the basis function which are given in W. So here, if the basis function in V is not standard basis, it is given something else, then also you know the concept that any basis function in V will be written as a linear combination of these basis function in W. So then T12 you will write as a linear combination. So this is coming as 3, 0, and this is coming. This is very simple, but just you have to understand what I'm doing is we are just writing as a linear combination, and then from there the coefficients will make your matrix A. So this this one you have to write. This is coming from my transformation which is given. So this 3, 1, 0, 0 minus 3 is coming from here. Now I will write 3, 1, 0. Now this is easy to write because this is my standard basis. And this is my minus 3, 0. So the matrix which I form is my this. This is very simple, but if you don't know how to do it, you won't be able to do it. That's it. This is my matrix. Yeah, anything you want to ask?
Ma'am, how you write B dash equal to 1, 0, comma 0, 1?
No, I am not writing. It is the question is saying that there is a linear transformation which is defined at this with respect to the basis functions which are given in V and W. Right? So this, even if this W was not given, I'm saying if something is not given, you will take it as a standard basis. But here they are saying this. Now a basis in V, so that the transformation you know is TV equal to W. Right? And what I'm saying is, you know that this, when it is the case, then each TV1 can be written as a linear combination of W1 and so on. You know TV2 can be written as a linear combination of these W1, W2. If you know this, then you know that these scalars actually are making a matrix A. Right? Now, the question is saying that with respect to these basis function, and this B is in V and W is in B dash is in your W. So that means what? You are writing TV1, TV1, you are writing as a linear combination of basis function which are in W, and there are the linear combination. And again, TV2, you are writing as a linear combination of basis function in W2, which is this given. Therefore, you are writing this. Now, the coefficient of these will make a matrix A because you know it from the early, and therefore this becomes the matrix.
Ma'am, we are writing the column space of the TV1 matrix in terms of the basis of W.
We are writing this here. That's all we are doing. This is the simplest thing, just that you should know how we are doing. This is how we are doing. You have a linear transformation with the basis is n and basis is m, right? Now B, you have a basis in V, you have a basis in W. Now this, because they are basis, then each element can be written as a linear combination of these. Each element can be written as a linear combination. This is the basis definition, right? If V1, V2, Vn are the basis, then any other element can be written as a linear combination. So if W1, W2, Wm are the basis, then any other element Tv1 can be written as a linear combination. Taking this, this becomes your matrix here, M cross N. Yeah, columns. Those columns are making the. So if you have these coming -3, -1 and -2, 2, their columns will make the matrix A. Similarly here, just that you have to see what is given, what kind of bases are given. If no bases are given, you take it as a linear standard basis function. So that was the first question we did, that V generally in the beginning, the V was not given. So that we were taking as a standard basis functions, and then we were writing as a linear combination. Right? So I am just assuming that the isomorphism and these non-standard bases are a little bit clear to you. But if they are still not clear, I will do again on Wednesday. I will come up with few questions, practice per question. We will do it here. And the entire linear transformation, we will bring questions so that we are doing it from the beginning and it is clear to you.